Hello guys, in this video we look into this question number 6, okay, from the handout which had been shared with you before. So one of your friend had asked me about this question, okay, so let's look into this question together. So with no radioactive sample present, a scientist records a background radiation count of 40 counts per minute. Okay, so for any question, if you find this statement without any radioactive sample, okay, with no any radioactive sample, and then we will get the readings, although there is no radioactive sample, that means this reading will represent the value for background radiation. Okay, background radiation. Okay, the scientist brings a radioactive sample close to the detector. The count rate increases to 200 counts per minute. Okay, so 200 counts per minute, it is the reading from the detector caused by first we have the radioactive sample, and then don't forget that we still have the background radiation. So actually this 200 count per minute is equals to the uh, radio radiation coming from the sample. So let's say radiation from the sample and not at that time, and then plus the background radiation. Okay, plus the background radiation. Okay, from the question we know that the background radiation is 40, so n naught plus 40. So that means we can find the actual value produced by the sample. N naught is equals to 200 minus 40, so we will get 160 count per minute. Okay, so this is the initial reading for the sample. And then after 24 days, so after 24 days, the count rate is 50 counts per minute. So again, this 50 count per minute, okay, 50 count per minute is actually the reading coming from the sample plus the background radiation. Okay, now I just put n here. Okay, so n naught represent the initial reading, and after 20, the reading after 24 days. So n plus background radiation. So background radiation, same for the same place. Okay, since the scientist is working at the same place, that means the background will be the same, which is 40 counts per minute. So n plus 40. So you can find the reading produced by the sample after 24 days. It is actually n equals to 50 minus what is the minus 40. Okay, so you will get 10 counts per minute. Okay, so now you have the initial reading and then the reading after 24 days. Okay, so this is the step that you should look into, or you should do before you do any calculation in your half-life. Okay, before you do half-life calculation, you need to subtract first the background radiation. Okay, the background radiation you need to subtract first. Okay, now you have n naught equal to 160 count per minute, and n after 24 days you will get 10 counts per minute. Okay, then you can do the process. Okay, you can do the process. First, maybe you can just sketch the diagram. Okay, n naught, which is 160, it will decay into half, which is 80, and then it will decay into half, which is 40, and then it will decay into half, which is 20, and then it will decay into its half, which is 10. Okay, so we will stop whenever we get the final value. Okay, here from the question, the final value is 10. So here we reach 10, so we will stop here, and then calculate how many half-life will be experienced by this sample. So we have one half-life, 2 half-life, 3 half-life, and 4 half-life. So that's mean the total time here from 160 to become 10, it is equivalent to 4 half-life. Okay, for 4 half-life. So what is the total time for the sample to give radiation 160 until it reach 10? Okay, it is given in the question. It is 24 days. So that's mean this 24 days is equals to the 4 half-life. Okay, so you can write it. Half-life is equals to 24 divided by 4. So you will get 6. And don't forget the unit, this. Okay. So why do we need to sketch this diagram? Because we want to find out how many half-life in the total time, in the 24 days. How many half-life in 24 days. Of course, you can also do a simple maths by dividing the number. Okay, the total half-life, the total time taken is 24 days, and then the half-life is equals to 4 half-life. Okay, so you will get the same value. So here you can write it. The half-life of the substance is equals to 6 days. Okay, 6 days. So that is how you can solve any half-life problems that involve background radiation. Okay, just you need just to be careful. You need to subtract the value of the background radiation first, and then you can do this half-life calculation. Okay, for subtract the background radiation first. Okay, that's all for this video, and thank you.